Hello everyone, I'm Junming Ma. This is my colleague Yancheng. We are both from Ant Group, and very glad to see you today. And it's a great pleasure to be here today. We are here to present the project of SecretFlow-SPU. Our project is a privacy-preserving machine learning framework that combines performance and usability. I will be covering the first half of our presentation, and my colleague Yancheng will take over for the second half. We'll go into the details of SecretFlow-SPU. Let's take a moment to understand the context of our project. Machine learning has changed our world in many ways. It has transformed the landscape of technology and impacted almost every aspects of our lives, from computer vision, natural language processing, to even drug discovery. As the popularity and the importance of machine learning continues to rise, so do concerns around data usage and privacy. While data is crucial for training high-quality machine learning models and enabling accurate predictions, it's also inherent sensitive. For example, biometric and financial data are very personal and requires strict protection. Governments around the world have recognized the need to regulate the storage and the processing of sensitive data, and have implemented laws and regulations such as the EU's General Data Protection Regulation, which places strict restrictions on how companies and organizations can collect, store, and process personal data. So here comes the question: who can protect our data while we still want to process them? And thankfully, cryptographers have provided us with a solution to address privacy concerns in data usage, namely secure multi-party computation. We call it MPC usually. This technique allows multiple parties to jointly evaluate a function without revealing any information except the final result. To better understand how MPC works, I prepare a demo to show you, but unluckily. So I will explain it from my words. Let's consider a simple example. Suppose Alice, Bob, and Charlie want to calculate the sum of their salaries without disclosing their individual salaries to each other. Each party starts by splitting their salary into 3 random values, sharing 2 of them with other parties and holding on to the remaining value. Next, each party computes the sum of their holding value and the 2 received shares. The intermediate results can be shared. Okay. Suppose Alice, Bob, and Charlie want to calculate the sum of their salaries without disclosing their individual salaries to each other. Each party starts by splitting their salary into 3 random values, sharing 2 of them with other parties and holding on to the remaining value. Next, each party computes the sum of their holding value and the 2 received shares. The intermediate results can be shared among the parties to construct the final results without revealing individual salaries to each other. Through this example, we can see how MPC ensures privacy and enables multiple parties to jointly evaluate a function without compromising the confidentiality of sensitive data. Expanding on the use of MPC, it also enables privacy-preserving machine learning. We call it PPML. This means that multiple parties can work together to train a machine learning model without exposing their individual training data sets. Alternatively, a model server can also serve requests from a user via the user's inputs remain confidential, and the model server's model remains secure at the same time. MPC provides a powerful solution to balance the need for privacy while still allowing collaboration and data sharing. MPC gives a secure way to compute functions and train machine learning models without compromising data confidentiality. Despite its benefits, incorporating MPC into PPML can be a challenging task. This is because MPC and ML exist in two distinct worlds with different focuses and priorities. The MPC community is primarily concerned with designing low-level cryptographic protocols to ensure secure computation. On the other hand, machine learning communities focus on high-level building blocks such as tensor compression operations to develop accurate and efficient machine learning models. The challenge lies in bridging these two worlds together. It requires a deep understanding of both MPC and machine learning, as well as the ability to integrate them in a way that ensures both security and efficiency. So to address this challenge, there are existing frameworks that attempt to bridge this gap between these two worlds. One type of this framework is general purpose MPC compilers, such as MPCs. These frameworks encapsulate cryptographic primitives into customized machine learning APIs, enabling efficient and secure computation. However, they may not be compatible with existing machine learning frameworks, which can be a disadvantage for those who are already familiar with and reliant on these frameworks. Let's take a closer look. This code is from MPC's example of training a neural network for image classification. The code snippet showcases how MPCs can be used to enable PPML. In this case, the neural network is trained on encrypted data, ensure that the privacy of the training data is maintained. The example demonstrates the use of customized ML APIs provided by MPCs, which encapsulate cryptographic primitives and enable efficient computation of machine learning tasks. In MPCs, if we want to build neural networks, we can use ops provided in the ML module. And training models, we can use optimizers supported by MPCs. And by using MPCs, users can benefit from the security and the privacy advantages of MPC while still being able to perform machine learning tasks quickly and efficiently. However, as mentioned earlier, this type of framework may not be compatible with existing machine learning frameworks, which can make it challenging for users who are already familiar with existing machine learning frameworks. For example, if users need a complex program like GPT-2 inference, they have to write them from scratch. The second type of MPC-based PPML frameworks are those similar to machine learning frameworks like TensorFlow or PyTorch. Examples of this include TF encrypted and Krypton. These frameworks are designed with machine learning users in mind and offers APIs that mimic those of TensorFlow and PyTorch, but with cryptographic implementations to ensure privacy and security. By providing familiar APIs, these frameworks allow machine learning users to easily incorporate privacy-preserving techniques into their existing workflows. This can be particularly beneficial for users who are already familiar with machine learning frameworks and want to maintain similar development practices. Let's take a closer look. This is a snippet from Krypton, example of training a neural network for image classification. Krypton is designed to provide users with PyTorch-like interfaces to make it more accessible for those already familiar with PyTorch. One key difference is that instead of using PyTorch tensors, users must use Krypton tensors, which have similar functionality to PyTorch tensors, including support for operations such as addition, multiplication, But crypton tensors are designed to support MPC, meaning that the data is encrypted before being processed. Besides tensors, users have to replace PyTorch operations with crypton operations, and users have to migrate PyTorch models to crypton models. While crypton may be similar to PyTorch, it's important to note that it's a different framework with its own set of APIs and capabilities. While it is designed with machine learning users in mind, it is not a replacement for PyTorch for complex programs like GPT-2 inference. Users may need to refactor their code by substituting supported PPML APIs. And most importantly, this type of framework normally is designed to mimic only one machine learning framework. As the need of PPML continues to grow, the question of whether we can efficiently run machine learning programs of mainstream frameworks, especially legacy programs, in a privacy-preserving manner becomes increasingly important. This is where SecretFlow-SPU comes in. My colleague Yancheng will show how SecretFlow-SPU provides a solution to this problem.
Hello, I'll do the second part. So to address the previous question, we implement a novel framework called SecretFlow-SPU. This framework contains a compiler capable of converting ML models into its own bytecodes. And then the bytecode instructions are subsequently executed by a high-performance runtime, which operate using a specific MPC protocol. The SPU framework ensures efficient and secure execution of ML models. So here is a more detailed view of current SPU architecture. So in order to efficiently chatter into multiple leading ML frameworks without significant effort, we need to select a unified path that is widely adopted in today's ML world. So among the various alternatives, XLA emerges as an acceptable choice that not only meets our specific needs, but also perfectly align with the prevailing trends in ML world. So by leveraging XLA, we ensure seamless integration and optimal compatibility within a range of ML frameworks. Also, its versatile nature allows us to streamline our efforts and reduce the amount of work required to support those frameworks. So this not only saves valuable time and also enhance the overall efficiency of our ML operations. So SPU's own compiler leverage XLA HO as an input, along with the visibility information of each input. Initially, it will perform a visibility inference on the entire graph, and then transform HO into its own privacy-preserving HO IR. And once the visibility information is available in the IR, the compiler then will execute some MPC-specific optimizations to enhance the efficiency and the performance of the computation. These optimizations are carefully designed to address unique requirements of MPC protocols and ensure the resulting code is optimized for secure and efficient computation. We'll talk about some of those optimizations in later slides. The executor is yet another crucial part of SPU framework. It plays a vital role by taking the bytecode generated by the compiler and executing it using a specific MPC protocol. The design of the executor prioritizes both performance and extensibility. It enables supporting for multiple protocols while achieving a high-performance execution. So in summary, the SPU frameworks aim to achieve three key design objectives. So user-friendliness. So the front end of SPU is designed to be intuitive and user-friendly by supporting multiple ML frameworks without a lot of code change. Second, the extensibility. The components of SPU are built with extensibilities in mind, and it's designed to support not only multiple ML front ends, but also multiple MPC protocols at the same time. And third is high performance. The entire SPU system is optimized for high performance, and we have several efficient execution strategies implemented to maximizing the computational speed and minimizing the latency. So we can say SPU acts as a bridge that brings the ML world and MPC worlds with a user-friendly and extensible high-performance framework. So it enables users to harness the power of privacy-preserving computation without compromising. So now let's take GPT-2 inference as an example to show how SPU is very user-friendly. So here is a code from plain text-based GPT-2 inference. The model is pre-trained. The model is pre-trained and provided by Hugging Face. In this example, so we first import the necessary libraries and instantiate the GPT-2 model and tokenizer. We then define the input text and tokenize it using the tokenizer, and then bring back the tokenized input as the JAX array. Next, we define a function named text generation and perform the GPT-2 inference using a greedy search algorithm. And this function iteratively predicts the next token based on the previous tokens until the specific length is reached. And then the output is stored in the output IDs. Okay. So here is the SPU version of GPT-2 inference. As you can see, the text generation part is the same. And the only difference is in the run part. Now let's take a look at the run part and side by side and look at the difference. Okay. So as you can see, we're just like a few more lines compared with the CPU version. So let's go through it one by one. So the first line runs a remote function on device named P1. In this example, we just use an identity function to convert a public array into a private data on device P1. In a more realistic case, this can be some data only available on P1. So keep in mind, the content of input IDs will not leave device P1. Caller will only get a meta array with only input data type and shape information. So the second line runs a remote function on device P2 that loads the model parameters. Then we have a next line, which SPU will compile the text generation function in a just-in-time manner and start running the compile code with the selected MPC protocol. So before SPU actually runs the generated code, P1 and P2 will generate the secret shares of their input data and send it to corresponding SPU node. So finally, the computed result is reviewed. One can also review it to only a selected party that all participants agree on, so the privacy and confidentiality of the data is protected. So these are the typical lines of code that one need to change to bring a plain text ML model into SPU. So since we choose XLA as our front-end input, so we can say once there is a way from the ML framework to XLA, we can run it on SPU. So for the backend, to make it easier to make contribution from protocol designers, we have adopted the concept of hardware abstraction layers in modern operating system. Our interpreter issues instructions that dynamically dispatch through HLA layers to appropriate MPC API. For MPC developer, that means they only need to focus on implement a small set of basic instructions without worrying about the high-level application. This also enables user to switch protocols easily by modifying a configuration instead of having to rewrite the entire code base. So next we're talking about the compiler. The compiler is a critical role in optimizing performance. And we have designed specific optimizations for MPC cases. Let's take two as examples. So the first optimization is on the left part of the slide. So it's a optimization path that simply reorder multiply operations. In the original code, there is a sequence of multiplication involve secret data, and public data. So this sequence will generate two secret truncations, which are expensive in terms of network communication. When compiler detects such pattern, it will simply reorder the sequence to public, and secret. This reorder ensures that only one secret truncation is performed, thereby reducing the network communication and improve the overall performance. The second optimization path is related to max pooling layers. Usually in a forward layer, the maximum values are computed within a window of a tensor, and then in the backward layer, a select and scatter will perform the same maximum value on the same tensor with the same window setup. Both operations need to find the same data. While this is typically not very expensive in plain text scenario, it becomes super expensive in MPC cases due to comparison in MPC is usually quite expensive because it involves network communication. To address this, the compiler rewrites the first reduced window to also return a one-hot encoded indexing vector that can be reused by the later scatter operation. This reduces the network communication and computation, thus improve the overall efficiency of the system. So on the runtime, we have some other techniques that implemented to improve the performance. The first is like vectorization. We bundle element-wise operations into tensor operations, which can distribute it across multi-cores. By doing so, we can fully utilize the available computation power on the system. So another technique is streaming. This simply involves dividing inputs into smaller tiles and then overlap the communication and the computation to hide network latencies during computation. So for performance evaluation, we compared SPU with sort of frameworks like TF encrypted, MPSPs, and Krypton, which span through two major kinds of MPC frameworks that we talked about earlier. The result shows SPU achieve the best performance in almost all settings with comparable accuracy of other sort of frameworks. So under one setting, SPU is up to 4.1 times faster than MPSPs and 2.3 times faster than TFE. Under WAN settings, under LAN settings, we are slightly faster than MPSPs and significantly faster than TFE. So that's all for today's presentation. Thanks for listening. Any questions?